Welcome to the course. I just got a message to update my Zoom client, so that's why I'm a few minutes late. So let's continue our lecture on control, because we need to get started on the next lab. So we are skipping the planning part and let's do the control lecture first, and then we'll do planning next. So control is the last step in the perception planning control pipeline in the autonomous vehicle. So we discussed the perception in the past few lectures. So, and then the planning algorithm should perform a high level or low level planning, and eventually produces a trajectory, a path with velocities at each time point on the path. So, and the controller's job is to follow the trajectory given by the planner. So there are many control algorithms. We mainly focus on PID control and MPC, the two most widely used control algorithms for autonomous vehicles. And also, we only give the basic intuition and avoid mathematical details. There are entire control courses, including the course offered at University on the mathematical derivations. So we'll give a high-level overview of the control theory, but not the details. So vehicle control in the overall big picture. So perception with neural networks, deep learning, and so on, and then you have done the object detection, recognition, segmentation, etc. So you have a list of objects and their locations. So the next job is to plan a path around the obstacles based on the traffic rules and so on. So when you have a path and a speed profile along the path, the controller's job is to to track the given trajectory, and based on longitudinal control, which is using your gas pedal and brake pedal to control your longitudinal speed, and lateral control, that is to turn your steering wheel to control the lateral direction. So, and when you have computed the control commands, for example, throttle angle, brake position, and steering angle, then you send them, the controller sends them to the actuation hardware to actually control the vehicle. So the feedback control problem is that given the system and the reference signal, find a control law such that the closed loop system is stable and follows the reference signal. So here's your reference. And say it's 50 kilometers per hour. And your current speed is perhaps 45. So your measured output is 45. So you have a 5 kilometers per hour error, and your controller needs to take some action to correct the error. And so it produces a acceleration command and increases the vehicle speed, and gradually the error reduces to hopefully 0. So PID control, you have the error term in here, and you have 3 terms. P is the proportional term with a proportional constant Kp times error, and integral term for integration over the error, and the derivative term for with the error derivative. And you add these three terms together to form the overall control input U to input to the plant process. So it's called a plant because control theory was initially developed for chemical plants, manufacturing plants. So that's why you have the name plant. So in the vehicle domain, the plant refers to the physical vehicle, the mechanical parts of the vehicle. So and then you have sensors to measure the plant state Y, which feeds back as a feedback signal to compute the error. So you have a closed loop control to hopefully reduce the error to 0 or close to 0. So from the equation here, error equals reference minus the measured measurement Y. So if the error is positive, it means that your output Y is too small. So you need to increase the control input. Here, the KP, KI, KD are typically all positive. So and vice versa, if your error is negative, you need to reduce the control input. So the proportional term, if you increase the KP term, it causes a faster response, but also you have bigger overshoot. So your starting state is here, and when you gradually issue your control input, it'll overshoot if your KP is too large. With K equals 1.6, you have a very large overshoot. So you have oscillations. So if your overshoot is too large, the system may become unstable. So but if it's too small, say K equals 0.5, the red line, then you don't have overshoot, but you converge to the steady state very slowly. Your system is very sluggish. So the K equals 1.1, the green line, a green curve seems to be the best trade-off among the performance and stability. So in terms of a vehicle, so if you have a very high P gain, then it oscillates around your set point, the center line of the lane. If you have a low P gain, then it converges very slowly. Medium P gain is the best. So the integral term takes into account history of tracking error and eliminates a steady state error. So with the integral term, Ki equals 0.5 is the red line, the 1 is the green line, and 2 is the black line. So increasing Ki causes increase the overshoot, but also more robust to disturbances. So if you have a low I gain, you may have a steady state error that's never corrected or very slowly corrected. If you have a very high I gain, then your vehicle trajectory may oscillate, similar to high P gain. If you have a very good I gain, then you can converge to your desired set point quickly without any overshoot. The derivative term increasing KD causes reduced overshoot and faster response. Has little effect on steady state. Its effect is mainly on the transient response. And KD, large KD, it makes it more sensitive to measurement noise. So So here, the low KD value, say KD equals 0.5, then it's called underdamped. It means that the oscillation is not damped. Oscillation is still there. If you have very high D gain, the KD value is 2, it's called overdamped. The system becomes a little bit sluggish. And if you have a very good D gain in the middle, it's called critically damped. So it means that it converges to the set point without any overshoot or oscillation. So here's a summary of the effects of PID gains. So increasing Kp and increasing Ki causes a rise time, assuming a step input response from 0 to 1. So the rise time will decrease with increasing Kp and Ki gains. And the overshoot will also increase. The system is more responsive with higher Kp and Ki gains. Whereas for Kd, it damps the response. So with a larger Kd, the rise time has a small change, overshoot is decreased. So Kd helps to reduce the overshoot. And also for settling time, increasing Ki causes settling time to increase, and increasing Kd causes settling time to decrease, and also steady state error. So Ki is used to eliminate the steady state error, and Kd used has no effect on steady state error because its effect is mainly on the transient state. So I have listed a few videos online. So this is a very good tutorial. I think we should watch it.
The technology being developed for driverless vehicles is pretty incredible. In the near future, there will be robotic cars traveling on normal roads with the safety and efficiency of the best human drivers. These autonomous vehicles use various sensors to be able to localize themselves in any environment. They are also then able to construct a detailed plan to get from their current location to any desired destination. This video will provide an introduction to how these autonomous vehicles are then able to follow their desired trajectories. Getting a vehicle to follow a trajectory may seem simple to those who have driven before, but is it? Let's take a deeper look at this in a lab setting. If we want to follow a line, but we are too far to the left, we turn to the right, and vice versa. But how much do we turn? If the steering wheel is turned a fixed amount to the left or to the right, the approach is called bang-bang control. For controlling a car, this doesn't actually work that well. The response is very jerky and uncomfortable for the passengers. Fortunately, we don't have to steer like this in a car, since there is a range of angles the steering wheel can take. One way to set the steering wheel angle is to use what is called proportional control. Rather than turn the wheel a fixed amount, proportional control steers harder the further away we are from the desired trajectory. We take a measurement called the cross-track error to define how far away from the desired trajectory the vehicle is. Therefore, the steering angle we use is this cross-track error multiplied by a scaling factor called the proportional gain. The range of values the proportional gain can take drastically alters the performance of the vehicle. As you can see from this overlay, the performance gets better as the gain increases, but at a cost. If you start too far away from the desired trajectory with a high gain, the system can spin out of control. With the best gains, proportional control returns better results than bang-bang control, but it still doesn't work that well. With proportional control, the car can be crooked when it reaches the center line. The result of this is that the controller will repeatedly overshoot the actual desired trajectory and not actually follow it. To correct this overshooting problem, we need to consider additional error measurements and use them to update our steering command. A good candidate for an extra measurement is to look at the cross-track error rate, or in other words, how fast we are moving in a perpendicular direction with respect to the desired trajectory. If we are perfectly following the trajectory, our cross-track error rate will be 0. In control theory, this is what is called a derivative term. This rate term can then be multiplied by its own gain and added to the proportional term to construct an updated controller. Now that we have two terms, we have two gains that must be tuned simultaneously. Conceptually, we can think that increasing the proportional gain will increase the pull that the vehicle feels towards the desired trajectory. Increasing the derivative gain increases the resistance the car will feel against moving too quickly towards the line. Fixing the proportional gain, if the derivative gain is too low, the system will be what is called underdamped and it will still oscillate. If the derivative gain is too high, the system will be what is called overdamped and will take a long time to correct for offsets. Properly choosing the derivative gain allows the car to approach the desired trajectory quickly with a cross-track error rate close to 0. This is called being critically damped. Despite the success so far, for a complete controller, we're not done yet. Environmental factors or mechanical defects can change the vehicle's nominal behavior and thus the performance of the controller. For example, if there is a heavy crosswind, the vehicle will drift unless the driver counteracts this wind force with a corrective steering command. Here is an example we can easily demonstrate. Imagine our vehicle is driving along and hits a pile of rocks, which knocks its front end out of alignment, and therefore a 0 steering command no longer keeps the vehicle driving straight. As you can see, with the controller that has been described so far, the vehicle experiences a buildup of a lane offset, or a steady-state error. One way to address this problem is to add yet another term called an integral term. This third measurement sums up the cross-track error to give an indication if we are spending more time on one side of the trajectory or the other. You can see that if we sum up the cross-track errors, we obviously spend more time on one side of the trajectory. The integral term we propose is then exactly this sum multiplied by a gain. Now, 3 gains will need to be tuned all at once, which can be quite difficult to do by hand. If the gain is too large, the controller can go unstable because normal controller fluctuations will be exaggerated. If the gain is too small, it can take too long to respond to these dynamic changes. When the gain is just right, the controller will be able to quickly correct for the front-end misalignment and return to its nominal performance. The combination of these 3 terms is then what is referred to in control theory as PID control. There are other more advanced controllers that can be used for self-driving cars, but they will all look similar to the one we have described in this video. There will always be some measurements made about the state of the vehicle, which are then compared to some desired vehicle trajectory to construct a steering angle that ultimately controls the car. Hopefully this gives some insight into the control strategies that can help make self-driving cars possible.
Okay, I hope that that's clear. So also another video here is also very helpful. So I like the comment here. So after watching countless PID videos, I only say that your video was the best. So yeah, and also the other video, the reader says, holy, this 12-minute was much more useful than my 2 semesters of control systems. So, so these teachers are very good in giving very good intuitions on the P, I, and D terms, what their uses are. So I highly recommend watching these videos. They're not very long. And also that video I just watched was on vehicle lateral control. That is, you're trying to track the center line of the lane. So the longitudinal control is similar. So you just need to track a given speed. So the vehicle lateral control, when you write it more formally, is to keep the reference trajectory as D is 0, which means that you're right at the center of the lane, and theta is 0, which means that you're pointing right forward. So at this point, you have a error in the lateral direction with this error, and also in the angle direction, you also have an error. So the D here is the cross-track error discussed in the video. So assuming that your vehicle is traveling at a constant speed VR, so the only controllable input is the steering angle. And you can issue a control input to the plant to track the reference trajectory. So that's just a formulation of the lateral control problem. So for this formulation, let's work out the equations. So first, we assume linear system dynamics. So the D, the cross-track error, dot equals V times theta. So it's actually v times the sine theta, which is approximately v times the theta, assuming theta is small. So this is a linearized kinematic model. And theta dot equals u. So the u controls the steering angle. So it controls theta dot. So with a P controller, you have a proportional terms. Here the k is a vector, multiplies the state, which gives you the control input. So the closed loop dynamics is obtained by plugging in the u into the equation here, and you work out the addition. You have this equation here. So in my PowerPoint, I have this dash, which indicates a second level bullet. So it's a little bit confusing because it's not a negative sign. And the reference trajectory is 0, 0. So in the center lane and going forward. Your error signal is the difference between the reference and your current true state. So which is minus your current true state vector. So the error dynamics is this E dot equals minus d theta dot. Just take a derivative of the above two terms on the both sides. And if you plug in the equation here, you get this. So now this is your error dynamics. That is how the error evolves based on your control input. And control input is expressed in the two proportional terms, KD and K theta. So your job, the control system engineer's job, is to design the KD and K theta to drive this error to 0. So if you're a control engineer, you do this in MATLAB. So you first perform work out the closed loop pose, a determinant of lambda I minus this equation. You get this and get the pose, and then you design controller to make a critically damped dynamics. So that your system converges to the steady state without any oscillation. So this is the formal mathematical way of designing a controller in MATLAB. So this is not covered in the course. So instead, in our exercise, in our project assignment, actually we use a more heuristic trial and error approach to controller design. So the linear system dynamics relies on the small angle assumption. That is, sine theta is equal to theta. So you need to set a threshold, a theta threshold, so that this assumption is valid. So to keep this assumption valid, you can set a this clipping operation. So if your D is higher than the threshold, you simply set it to D threshold. If it's lower than minus D threshold, set it to minus D threshold. If it's within this bound, then you do nothing. So this ensures the small angle assumption is valid. So here is the if you have the theta threshold is pi over 6, then you can set the D threshold to be this term to ensure that the small angle assumption is satisfied. So this has the effect that even if the vehicle is very far from the center of the lane, do not change the heading angle theta too fast to keep the small angle assumption valid. So it's a rule of thumb. So if you go back to the system equation here, we made an assumption at this point. So this assumption requires a theta to be small. If you don't remember theta is the steering angle. Your steering angle, your wheel direction versus the forward direction. So so by imposing this constraint, you are really making the controller pretty conservative. So even if you're pretty far from the center of the lane, you are still making small adjustments. You are still turning your steering wheel at a very small angle to keep the controller valid. So there are many assumptions we made in the previous controller design example. So we did not consider uncertainty due to measurement noise. So we assume perfect state estimation, where d hat and theta hat, the estimated state, is equal to the actual state. So in fact, in reality, you have a common filter, particle filter, and a bunch of state estimation methods that try to minimize the estimation error, but your estimation will never be fully equal to the true state. And also estimation latency. So time from the measurement to the state estimation available to the controller. So this is the execution time of the filter algorithms, and also constraints such as actuator limits. We may need to impose a maximum curvature radius to simulate a real car. So a real car can turn at a maximum angle. You cannot arbitrarily turn at very large angles. So a discrete time assumption. So we have a multi-rate, non-uniform sampling, but so the controller design in MATLAB is typically in continuous time, but the actual implementation on the automotive ECU, automotive computer, runs in discrete time. So you need to set a sampling rate. So the sampling rate of the estimator is typically slower than that of the estimator. The common filter and so on is typically slower than the actuation, which is it's really approximating the continuous controller. So that's a very brief introduction to PID control. In automotive industry, PID is perhaps 90% of the control theory you need. And MPC makes up perhaps the rest 9%. And perhaps 1% is for the other control algorithms, more advanced control algorithms. So the control in automotive systems is a relatively mature topic. So it's just dominated by PID and MPC, these two algorithms. And these two are very old. So generally people view it more as engineering than research. So the research frontiers are mainly in the perception and planning part, where a lot of AI, machine learning is involved. Whereas for control, people generally view it as a solved problem. So unlike aerospace, if you're controlling a fighter jet or a fast drone, so the aerodynamics can be very non-trivial and very hard to control. Whereas for ground vehicles traveling on paved roads, generally the control is not a hard problem. It's viewed as a solved problem. So yeah, it's not an active topic of research. So the next controller we'll introduce is MPC, Model Predictive Control, also called Receiving Horizon Control. So you have a physical system or plant, and your controller runs a inner optimization problem at every time step. So you have a prediction horizon M time steps and control horizon P time steps. So at every time step K, you set the initial state to predicted state as K and solve a constraint optimization problem over a lookahead window K to K plus M to get a sequence of control inputs U while in the time interval K minus 1 to K. So U is applied for this current time step from K minus 1 to K. And so maybe a picture is a better explanation. So your current time step is K. So right now you're at time step K. And you look forward a control horizon P and a prediction horizon M. So and you solve the optimization problem and get your control commands U for the future P time steps. So you look ahead for M time steps and compute a series of control inputs for the future P time steps. Typically K equals P, but you may also set K to be less than, P is equal to M. That is, the control horizon is equal to the prediction horizon. But also it's possible to have P less than M, as shown in the picture. So the control inputs UK to UK plus P minus 1 is the dotted line in here. So you compute a series of control inputs, one for each of the future P time steps. But you only apply the first one, the current one at the current time step. And then you move forward to the next time step, K plus 1. You perform another look ahead and optimization to get another series of control inputs for the next P time steps. However, you only apply the first step and so on. So at every time step, you look forward for a time horizon, prediction horizon, and solve for a series of control inputs for a future horizon. However, you only apply the first one and discard the rest because the control inputs are computed based on the assumption that your system has a certain dynamics. However, as you move forward in time, things may have changed during the time step. So that's why you need to update your compute a new series of control inputs. So this is a feedback control because at every time step, you're taking into account new information from the sensors to compute a new command. So if you had if you just applied the computed P control inputs blindly without any updates, then it's an open loop control. So it's a closed loop control because you're always taking into account new sensor information at every time step. So here's a illustration of MPC. So suppose this car, your ego vehicle, is stopped here. So and your planner has given you a trajectory. So this blue is the desired trajectory, and you need to the controller's job is to track this blue trajectory. So based on MPC, you solve for the control inputs U for the future time horizon big T to track the blue trajectory. And because this vehicle may have initial speed, maybe in this direction, so it's not possible physically to completely track the blue trajectory accurately. There may be some deviations. So suppose the the red line is the computed future trajectory in a look-ahead window, and then you apply the first UT at the first time step, at the current time step. So now your vehicle moves forward based on your control input UT. It goes a little bit forward to this position now. And then at this position, the vehicle replans a new set of control inputs at the new current time step, the orange line. And then you apply the first control input and move forward, and so on. So this is the process of MPC control. So here's an example of MPC control in action. So this is Udacity's driving simulator. So I mentioned before, Udacity has this course of self-driving car engineers. So they have the simulator and some assignments for doing MPC control. So the yellow is the reference trajectory from the planner, and the green is the trajectory from running the control inputs U in the future T time horizon big T, computed by MPC based on the system model for look at horizon T. So you can see that it tries to track the blue trajectory, but it can't based on the dynamics. So at every time step, you apply the first control input, and next time step, you replan. So here's the mathematical formulation of MPC. So you have an optimization objective J. Suppose you first, let's consider a linear MPC with no constraints. So the objective tries to minimize the first term says that you minimize the difference between the actual state and the reference state. And the second term says that you should minimize the control effort, U. And also your deviation from the actual state and reference state along the whole trajectory. And the matrices Q and R encode the relative importance of the two objectives. So if your Q is very large, then you really care about tracking the trajectory accurately. You don't care how much actuation effort, how much gasoline you need, and any concerns over control input. If your R is very large, then it means that you care about your control input. You should minimize your control input. You should try to save energy. So the setting the relative magnitudes of Q and R allows you to perform trade-off among the performance and the energy efficiency. So so this is the optimization problem, and this T time is from the current time to a future window of a big T. So and you have system dynamics, which is linear. Next state is equal to A times the current state plus B times the control input. So X is the difference between actual state and reference state. So you can solve this problem analytically by using called linear quadratic regulator method. So this is a proportional control no, it's not. So this x may be a vector of state and state derivative and so on. So this could be a PID controller. So the k could be a vector of p, I, and d terms. So so you can solve it analytically with the linear MPC formulation, but with the nonlinear MPC, where the system state xj plus 1 is a nonlinear function of the state x and control input u, and the cost function may be also nonlinear, and also you may have constraints on state x and control u. So for example, the u may have a upper bound based on your physical limits of your actuator. Could be your steering angle, maximum steering angle, or maximum acceleration, and so on. So given these, and also some general constraints on xu with the equations based on g and h. So so for this general nonlinear problem, you cannot solve it analytically. You can only solve it numerically. So there are nonlinear solvers, but they are often not fast enough. So there has been a lot of research on solving MPC very fast in the online manner. But I won't discuss them here. So the notation is a little bit confusing because in the x term here, the subscript denotes the look-ahead horizon from the current time step, whereas the superscript denotes a vector transpose. So MPC is so-called predictive control with a look ahead. So you're looking ahead at time horizon and performing control based on your information in the future time window of length t. Whereas compare this to PID control. So some people have said that PID control is like driving your car by looking in the reverse rear view mirror, because you are not looking ahead. You're only making a decision, control decision based on your current state, which is determined by your past. So in this sense, MPC is a more advanced control algorithm. And also it handles constraints explicitly, whereas PID control cannot handle constraints. By constraints, I mean here, the x and u can have lower and upper bounds and may have general g and h constraints. So, and also MPC is applicable to both linear and nonlinear systems, whereas for PID control, the pole placement method is applicable to only the linear systems. So the cons are that the optimizer computation may be expensive, especially for a nonlinear MPC. So MPC was initially developed in the process control industry, that is in the chemical plants, where you are controlling the chemical reaction systems, and the look-ahead horizon may be a few hours or even a few days. And you're issuing a control command maybe every half day or every 4 hours. So in that sense, MPC is not a real-time algorithm. You can compute it very slowly, solve the optimization problem in an hour. That's still okay for process control. But when you apply it to automotive control, the time horizon becomes milliseconds. So if you want to control your actuators 30 times per second, then at 30 hertz, then you only have 33 milliseconds to compute a command. So by moving the MPC from a very slow scenario in factories to a very fast application scenario in cars, there had been a lot of research on making MPC faster. So yeah, there have been a lot of advances in the algorithm side and also on the hardware side, as the high performance ECUs are used more and more in cars. The computing power is also increasing. So the combination of algorithm and hardware advances makes MPC applicable to automotive systems. And also the look at horizon T can be selected to trade off between the control performance and computation overhead. With a larger T, you have better control performance, but a higher control overhead, the computation overhead. And also, it requires accurate yet efficient system model. Then, as a control engineer, you need to develop a model for your plant, the mechanical part of your car, perhaps by system identification, before you can apply MPC. Whereas a PID control can be applied even without a model. So, we will see in our project, you can apply PID control. If you had a model of the system, then you can apply pole placement and other methods for controller design, and you can have rigorous guarantees. But if you don't, you can just apply PID and tune the PID gains heuristically, and oftentimes it works pretty well. So here's a example of MPC for vehicle lateral control. So the vehicle, the physical vehicle is the plant, and the cost function is trying to first minimize deviation from desired reference trajectory, and second is to minimize control effort. So that is the two terms here. So the first, the Q times X terms is trying to minimize the deviation from reference, and the U times R term is used to minimize the control effort. And constraints are system dynamics, longitudinal and lateral, and tire force constraints. And MPC controller is the high-level controller that issues the longitudinal force and lateral force outputs, and then it's fed into the low-level controller as input. Low-level controller takes into account the engine map, that is how much force can the engine produce by controlling the gas pedal. So, and also the actuator models, the physical part of the actuator, and also the physical model of the tire. And then it issues the throttling, braking, and steering commands to the vehicle. So we have a hierarchical control architecture here, where MPC is a high-level controller that issues high-level commands, whereas the low-level controller is essentially a lookup table-based controller that issues the low-level actuator commands. So you can also integrate the low-level controller into the MPC, so the overall MPC performs the mapping from the error to the throttle and the braking and steering directly. So it has more complex models and constraints with increased optimized computation load. So it just shows some performance from the actual experiment. So consider a passing maneuver. So the ego vehicle turns left and tries to pass a front vehicle, and turns right to return to the ego lane. The lateral distance initially it's a 0. That is, you're initially at the center of the lane and you turn left. And after you pass the front vehicle, you turn back to the center lane. So the velocity, longitudinal velocity and lateral velocity as shown in here. So you can see that the blue line describes the actual vehicle state trajectories. That is the lateral position y, longitudinal and lateral velocities. Yaw rate, yaw is just a term for describing the steering angle rate, angular velocity, and it tracks the reference pretty well. Reference is the red lines. So this example is taken from this Coursera course, which I have a link on the homepage. So here's the quiz. So which statements are true about MPC? All of these are true. First, horizon is a finite window of time. Prediction horizon keeps being shifted forward at each time step. And the full optimization over the time horizon is performed at each iteration. And also only the first control action from the optimization is applied at a time t. So all of these are true. So let me explain the terms of kinematics and dynamics. So kinematics is the study of motion without considering the forces that affect the motion. So it deals with the geometric relationships that govern the system. So for example, kinematic model is x dot equal to v. The distance derivative with regard to time is a velocity, and v dot is equal to a. The derivative of the velocity is the acceleration. So it uses position, velocity, acceleration as a control input. So there's no dynamics involved. Whereas dynamics is the study of motion tracking, taking into account the forces that affect it, described by the equations of motion. For example, Newton's law with friction. So the force is equal to mass times the acceleration plus b times the velocity. So the first term is the Newton's law for F equals ma. The second term is the friction term. So it uses a force and torque as control input and takes mass and inertia into consideration. So let's use an example. Consider two vehicles with the same geometry but different mass and weight turning a tight corner. So the vehicle, because they have the same geometry, they may have the same kinematic model but different dynamic models due to different mass. So if both are controllable kinematically by control input A, but they may not be controllable dynamically. So the light vehicle may be controllable dynamically by control input, whereas the heavy vehicle may not be controllable dynamically. Due to the large mass, F may exceed the max actuator limit. So a small vehicle may turn a sharp corner easily, whereas a large truck may not be able to turn a sharp corner due to the larger mass, the larger inertia. So that's a difference between the kinematics and dynamics. So this is an orthogonal issue from control algorithm. So PID or MPC may be either based on kinematic equations or dynamic equations. The algorithms can be applied to both situations. So here's the illustration of kinematic versus dynamic control. for the lane tracking controller. So you may have a controller that produces the control input to the plant, which is the heading angle rate, theta dot, and velocity, which is constant here because we're only controlling the lateral motion. This is the kinematic control. So by the way, the heading angle is controlled indirectly by the steering angle, which we'll discuss next. Whereas this example is a dynamics control example, because you are taking into account the vehicle's dynamics. So the control input from the MPC is the longitudinal forces, and control input from the low-level controller is the throttling, braking, and steering. So, in reality, the controller is always a dynamics controller, but kinematic control may be an abstraction, a more abstract form of control that's used in the early control design stage. So we will discuss our lab next. So before we take a break, any questions? Okay, let's take a 10-minute break. the upper bound, you're at in this time interval u. Essentially, force applied, and then you will compute the derivatives of the. Okay, for the next part, I'll discuss the PID Control Lab. So this lab is based on the Coursera Audacity course, AI for Robotics, PID Control. So it's a lateral control of a car to run along a racetrack, so which can be a straight line or circular with fixed speed. So you're only controlling the steering angle. Instead of me describing the lab, I'll be lazy and reuse my lecture from last year. So let's watch my last year's video, which is online, available from my course homepage. It's lecture 3, control part 2. To run along a racetrack with a high level. So here's the lab 1. Lab 1 is to perform lateral control of a car to run along a racetrack with fixed speed. So here's the racetrack, and then you will compute a cross-track error based on the distance from the track. And then this is the error term used in PID control. So the problem specification is clockwise traversal. So you are going in a clockwise direction. So for this clockwise traversal, CTE is higher than is positive if car is outside of the track region, negative if inside. So here's the kinematic bicycle model. Assuming front wheel steering. So and then the rear wheel is the reference point. It's possible to use the front wheel or the center of gravity as the reference point to get different equations. But for this setup, we consider the rear wheel as the reference point. And then state vector is x, y, theta. X is the position of the rear wheel. Yeah, I think it's better to mark it here. Position of the rear wheel and heading angle theta. So control inputs are the data, steering angle, and vehicle speed v. V is along the vehicle's body direction in this direction, and heading angle theta. So typically angles, steering angle delta and heading angle theta are based on clockwise convention with regard to a reference direction. For example, the steering angle, the wheel direction is with regard to reference direction of the velocity v. So that's the vehicle's body direction. So that's delta, the angle between the steering wheel direction and the vehicle velocity. The theta is with regard to reference direction east for this example, which is horizontal. And then any rotation angle, the rate is higher than 0 for clockwise rotation. And then these are the control inputs. Control inputs are delta, where you can turn the steering wheel, and velocity, where you can accelerate or decelerate. So there's a relationship between delta and vehicle length, the distance between the front and rear wheels, and the instantaneous center of rotation, the radius for the instantaneous center of rotation. So the reason that this relationship holds is that if you look at the diagram here, the rear wheel's direction is perpendicular to the line from the ICR to the rear wheel. And the front wheel's direction is perpendicular to the line from ICR to the front wheel. Therefore, this angle here is delta, because both of the lines are perpendicular to the other two lines that define delta. So once you have this relation, you can derive that tangent delta is L divided by R based on this triangle relationship. And then once you have the angle delta, you can derive the rotation rate of theta. Theta dot is often written as omega, the angular velocity. Yeah, rotation rate should be really angular velocity. So it is speed times the rotation radius. So the vehicle has a speed in this direction, and then it's performing a rotational motion. So the rotational radius is r. Therefore, the angular velocity is the vehicle velocity times the rotation rate divided by rotation radius r. So that's pretty much the definition of angular velocity. So how fast you're traveling and how large the circle you're traveling on is. And then you plug in the relationship here because this r is a derived quantity. So and it's changing all the time as you're turning in different directions. So and then you plug in r from this relation, you get this relation. So this relates the angular velocity to the vehicle speed v, steering angle delta, and vehicle length l.
I'm sorry, shouldn't it be kind of factor 2 pi or something?
Oh, the 2 pi is already factored in because the theta is expressed in radians, not in degrees. In the Python code, there's a factor of 2 pi. But yeah, if you express the angles in degrees, then you need to have a factor 2 pi.
Well, in degrees would be 360, or the velocity is meter per second, and this is meter, this is per second, and there's number of rotations per second. And that velocity, one rotation should be 2 pi or something. Yep. Okay, don't care. So, or is the velocity measured in something other than meter per second?
Velocity is meter per second.
And this is meter.
Length is meter.
So this is per second.
Yes. Or you can say radian per second.
Isn't it turns per second? Maybe it's radians. Okay, sorry.
Radian per second.
Maybe misunderstood something. Yeah.
Not turns per second.
Okay.
Yeah. So if you write out the state equation in matrix form, in the vector form, you have this equation. X dot is v times cosine theta, which is, so the x velocity in the x direction is the v times cosine theta, the projection of velocity to the east direction. And in the y direction, in the north direction, you have v times sine theta. And then you have this relation theta dot equals v times tanh c delta or divided by L. And then the system control inputs are v and delta. And then you have this nonlinear system model. So and given the system model, how do you get the updated equation? So these are the updated equations. So first, let's look at the streamline motion, which is a straightforward translation of the system equation by propagating one time step dt forward. So this is straightforward moving forward one time step dt. But this only holds for small theta dot times dt. It's described as straight line motion, but it's approximate because the real motion is rotation along a instantaneous center rotation ICR with a radius r. So for the accurate description of the circular motion around ICR, you have this equation where the r is derived from the previous relationship here. So in the Python code, the derivation is quite clear. So let's go through the Audacity's Python code for computing the vehicle motion. So these steps are to apply noise. These are useful for state estimation, which we did not discuss in this course. That is common filters and particle filters. So these are not relevant to us. So we set them to all to 0. And then we execute a motion if the so the turn is the turning vehicle turning angle, the change in theta in the time step dt. So that's theta dot times dt. And then if the change in vehicle heading is small, if absolute value of the turn is less than the tolerance, you can approximate this motion with a straight line motion with the equation we saw before, the approximate equation. So here you see in the code, they have this pi, 2 pi. Oh yeah, so they have this modular 2 pi. Actually, yeah, because if it's higher than 2 pi, you just subtract 2 pi. This doesn't change the any operation. So then for the circular motion, the way the computation is done is to first you derive from the rear wheel position xy, you derive the coordinate of the ICR, instantaneous center rotation cx and cy, based on this formula here. The reason, again, look at the angles. This particular angle here is theta because of the perpendicular relationship. So this line here is perpendicular to the east line, east horizontal line. And this line here is perpendicular to the vehicle length. Therefore, this angle here is theta. So the coordinate of the ICR, the x coordinate is the vehicle to rear wheel position x coordinate minus a r radius times sine theta. So this this term here, based on the triangle here, and y position of the ICR is the vehicle rear wheel y position plus r cosine theta. That's the length here. So once you derive the ICR's coordinates, you can perform a rotational motion around this ICR for a angle of turn theta dot dt. So you add the theta dot dt to the current vehicle heading to get the new heading. That's the orientation or heading of the vehicle. And then based on the new heading, after adding the turning angle, you get a new coordinate after rotation, which is from these ICR's coordinates, you perform reverse derivation to get the XY coordinate of the rear wheel. So perhaps there's a small rotational motion, and then the new position is perhaps in here. And this angle here is theta dot dt. So that's how you get the updated equation here. So you first perform a subtraction to get the coordinate of the ICR, and then you perform a small rotation with a small angle here. It doesn't have to be small, it can be large because this equation is accurate. And then you perform a reverse transformation to get the XY coordinates. So is this derivation clear?
Yes.
Okay, very good. So I'm just looking at the derivation to see if I need if I missed a 2 pi somewhere. The modular 2 pi, do I need that? Well, I think you don't need it because you're performing the theta with cosine and sine functions. So even if you have the extra 2 pi in there, it wouldn't change the result. Yeah. So in the Python code, they have this modular 2 pi, but if you remove it, I think it's fine.
It's just if you turn several rounds, so you don't end up in like 100 pi or some strange angle.
Yeah, but even if you have 3 pi, that's fine because at the end you're taking cosine and sine functions.
Yeah, so it shouldn't matter.
So here's a little bit derivation, not that important, to show that the straight line motion with a steering angle delta is 0 is a special case of circular motion. So equivalent to a circular motion with radius infinity. So first, let's look at delta goes to 0, then the rotational radius goes to infinity, and theta dot, the angular velocity goes to 0. So which is intuitive because small steering angle delta leads to slow turning rate, slow angular velocity. That's the better term. Oh, okay, yeah, theta dot. And then we get a special case for the straight line motion to improve computational efficiency for small delta and theta dot, and also to avoid division by 0. However, you can derive the special case from the accurate general case. So here's the accurate equation here, and then you realize that this term here is actually the derivative sine function times the theta dot dt. So that's pretty much definition of a derivative, assuming that a straight line connecting the starting point and end point, and then the derivative is the slope of the line. And then you plug in this term into the equation, and you cancel out the theta dot term and get the this term, which is the term for the straight line motion approximation. Now, similarly for the y term, you get the y motion as a special case of the circular motion. And you can check the validity of these equations. So if theta is 0, theta 0 means that the vehicle is the heading is horizontal or east-west. That's the vehicle heading with theta 0. And then you're traveling east. So the x is updated at every time step, and y stays constant. Sorry, missed the dt here. And then if theta is 2 pi, it's pi, and then you are moving west. If theta is pi over 2, you're moving north. So by plugging in the equations. So in the Python code, the run function performs a PID control operation to define the steering angle direction delta, and then you do a move operation, which is the bunch of messy equations we saw just now. So to get a trajectory, that is the actual trajectory traveled by the robot. So notice that the control law here, we have a minus sign at every term. So it's designed for the clockwise travel direction. With this particular definition of control law, you get the effect that if CTE is positive, which means that the car is outside of the track region, the control law will cause the steering angle delta to decrease. The car turns right, and vice versa. So if you look at the track, so if you're somewhere in here, the vehicle is turning in a clockwise direction, and then if it's here, then it should move. It should turn in this direction to go back to the track. If it's here, then it should turn in this direction. In both cases, if you're outside the track, then you should decrease the steering wheel angle. And then what does it mean to decrease the steering wheel angle? Remember that the angles are defined based on counterclockwise convention. So by decreasing it, we're turning right. So, and then if you're inside the track, we need to increase the turning steering wheel direction, which means that we're turning left. So we are inside the track and we're in this direction, and we need to turn left to go back to the track. So all of these definitions are coupled. So it relies on the assumption, first, that you're traversing the track in a clockwise direction. Second, your convention is that the angles are based on a counterclockwise convention. And then your control law looks like this. If you change any of the factors, if you travel in a counterclockwise direction along the track, or if your convention for calculating the angles is clockwise convention, then the equation wouldn't be right. You're missing a minus sign.
I have a little question. So this is on the global coordinate system, XY. So I think in a vehicle, you have just some kind of local, the street turns right or left or something.
So the vehicle state, x, y, and theta state vector is in a global coordinate. So somewhere you have a global 0.
Some GPS positioning or something. Yeah.
Yeah. So somewhere you have a global point of 0, and somewhere you have a global direction of 0. For example, east. So no, it doesn't matter how you define the global coordinate. The point is that they're global. They're in reference to a global reference frame. And then the steering angle delta is in reference to the vehicle's heading direction. So delta is kind of in a local frame.
Yeah, and the error is if you're kind of to the left of the road or to the right of the road. This on the next slide.
The
CTE is
the CTE,
like if it's larger than 0, you're to the left of the road. And if it's less than 0, then it's
not to the left, but to the outside of the track. So it's here and it's here. A CTE is all positive. If it's inside, it's negative.
Yeah, but on a random kind of track, it means you are to the right of the desired position. So you should turn left.
Yes.
And vice versa. So it's not connected to this particular racetrack.
With the assumption that you're traversing in a clockwise direction. If that assumption is reversed, then you need to reverse the sign.
Okay.
Right?
So,
because
but then the speeds are negative or okay, don't. But if you look in a local frame, so if you got the error positive, okay. In a real situation, you have the sensors and all this stuff with local facts.
Well,
data.
Yeah. So in a real car, the delta is measured by a local sensor relative to the local frame. But theta and xy are global coordinates.
Yeah. So if you're in to the left of the road, it's natural to turn right, so to say, locally.
That's only when you are traversing in the clockwise direction. Suppose you reverse it. Suppose you traverse in the counterclockwise direction. Suppose you want to drive in this direction. And then if you're on the left of the road, you want to turn left to come back to the track, right?
No, in that case, you are on the right of the road, to the
in the right.
of the road. Yeah.
And then you try to
turn left.
Turn left. Oh, yes, that's right. Yes. Okay. So in any case, I hope this bicycle model is clear. And the twiddle, let me explain this in detail. So let me finish this before we take a break. That's where I cut the video because I want the videos to be in segments, where each chapter is a segment, which is easier for you to look up. So the twiddle function, just the three PID parameters in turn. The P is in here. It has three control parameters, initialized all to 0. So length P is 3. You have PID 3 parameters, and then you update the P with dP, kind of like a gradient descent operation. Increment PI with amount dPi, and you run the robot for 2n time steps in this program. You compute the error. If the error compared to the previously best error, if it decreases, then it means that our adjustment of PI is in the right direction. So this is the right move. We're moving in the good region of the parameter. And then we save the current error as the best error, and then increment the step size. So we're moving in the right direction. We go in a bigger step, not time step. Otherwise, if the error has increased after you made the adjustment, it means that you adjusted in the wrong direction. You shouldn't have done that. And then you reverse and adjust in the opposite direction by adding -2 dp. So you're stepping in the opposite direction, starting from your initial position with the step size dp. So by doing this, and then yes.
Can I have a little bit comment on this as well? Sorry, and that is if you work with control, if you start with a p-value, the proportional part, and it works okay. But then when you add an integral part, you have to reduce the proportional part to keep stability in a control system. You know, you can't select the best p with the integral part to 0, because then when you increase the integral part, you have to reduce the proportional part. So this, for me, seems a little bit strange that you first set the p and then the I and then the d, because then afterwards, if you add the differential part, then you can increase the proportional part. so they are kind of connected, those parameters. But maybe I misunderstood this twiddle algorithm. But for me, it looks like it sets the first one first, and then the second one, and then the third one.
No, you didn't misunderstand it because the author, Sebastian Thrun, who is the voice in the videos I showed before, he was the first he was a Stanford professor. He worked in the DARPA Grand Challenges and then got a position in Google to direct the self-driving car project. And then he quit Google and started Udacity as his startup. So Sebastian Thrun is a roboticist. He's not a control theorist. Maybe if Sebastian talked to Carla, he could have realized that this issue.
Actually, I talked with him like 25 years ago in Switzerland. And we were talking about reinforcement learning at that time. So we'll mention that a little bit more later on. But he's a very good guy. But as I mentioned, we should have Leonid here. Maybe he could also comment on this. But this is a good, it might work okay. But from a strict control point of view, you should kind of adjust them all at the same time in some way.
Yeah, so twiddle is strictly a heuristic. So obviously you can add additional rows to the heuristic. For example, the row of decreasing t parameter when you increase I parameter. So all of these can be added. So this is just a very simple heuristic.
Yeah, sure. Good enough, I think.
Yeah. So let's continue. Now, at this point, we realize that we adjusted in the wrong direction. We have reversed directions. Now what? Okay, now we run again. Run robot again and get a error term. If the error decreases, it means that the reverse direction is okay. We are in the right direction. So we keep the error as best error and again, increment the step size. Otherwise, we are in the wrong direction. Now what do we do? So we could just reverse directions, but then you may be reversing and doing oscillation, never making any progress. So if you're always reversing, then the P pretty much stays around the same place. To avoid oscillation, we don't reverse the direction. Instead, we adjust the step size. We reduce the step size. So that's the reason why we're not reversing direction here.
And I noticed, sorry for my comment again. So we have this for loop where you adjust those, but then there's the outer while loop. So you redo the P adjustments after you have selected a integral part. So it should work okay. So no, there is an inner loop for E in range, and there is an outer loop while some dp is greater. And when it runs the next while, it redo this
yes,
adjustment of the P again.
Yes. So you're doing adjusting P, adjusting I, adjusting, I'm sorry, P, and then D, and then I, because the parameters are proportional, derivative, integral in that order. So, and then you are repeating the process until you get a some dp does not exceed a tolerance, which means that your step size is so small that you're not adjusting anymore. Then you stop. Okay, any questions on this twiddle function? So a twiddle versus pole placement. So twiddle is like a gradient descent approach to tuning PID controller. Notice that the controller design is based on the accurate bicycle model, which is highly nonlinear. So this is the bicycle model with the sine, cosine, tanity in there. So it's nonlinear. So even though it's nonlinear, PID can still be applied, except that you cannot use the pole placement, the control theory to design a PID. You must tune it with a heuristic rule because of the nonlinearity in the system model. Therefore, with this twiddle, it's universally applicable to any system by gradually adjusting the parameter with adaptive step size dp until convergence to a minimum best error given the DT's DP's upper bound. So when DP's when the parameter P's step size adjustment size DP stops changing, you stop. So it's a very generic approach to tuning controllers, whereas previously we saw the pole placement approach for PID control design, where we did approximation, where sine theta is approximated as theta with a small angle assumption. And additional simplification is to assume that the angular velocity theta dot can be directly controlled. So theta dot as u, the control input, instead of delta. So we are completely ignoring the bicycle model's steering angle variable. We're assuming that somehow we have a magical vehicle where we can directly control the heading, which is not realistic for bicycle model, obviously, but it's a simplification. So so in the course video, there is an error. So if you watch the video at this link, he said that if you set these two parameters, say KD, KI equals So let's stop the video here. I had 2 lectures on control, lecture part 1 and part 2. So I went into much more detail than this year. Yeah, actually it's not an error. So I realized that later. So in the Python code, if you set the D params 1 and 2 to 0, it turns into a P control. So So this is how you switch between P control, PI control, and PD control. That is by setting some D params to a constant 0. So a twiddle is a local optimization algorithm. So performance is dependent on parameter initialization. And this code is all initialized to 0 for simplicity, but you can try different initializations. Just like in a neural network, you can try to initialize the weights in different ways. This is the explanation of the program. Let's continue. First, change the track shape to a round circle with radius 50. So you need to modify the function CTE. The reason I did this is because I wanted you to know how to set the CTE function. Actually, it's not important. You could have used the original track shape. So, and then modify the twiddle to tune a P controller holding the KD to 0, and PI controller holding KD to 0, PD controller holding KI to 0, and then a full PID controller. So initialize the parameters all to 0, and then you can adjust the twiddle function to realize these different controllers. So the part 2 is to set a very high vehicle speed. So the original vehicle speed is 1 in the Python program. And then if you set it to 10, you may lose control, no matter how hard you tune. So after the twiddle procedure finishes, you get the set of parameters, PID control parameters, but the control performance may be very bad. And then to keep control, you can either increase the track length by increasing circle radius. Obviously, you run a larger track, that's fine. Or you can reduce this time step size, dt. That's the sampling rate for the controller, with a proportional increase of n, where n, 2n is the simulation time steps in run function. If you do these two changes simultaneously, you can keep the local simulation time constant. So let's take the latter approach and tune a PID controller with twiddle for speed equals 10. Try different time step sizes, dt, until you get a low tracking error. So if you look at the PowerPoint in this description of the bicycle model, I said the Python code assumes controller time step dt equals 1. So I have dt in my formulas, but it's not, dt is not in the code. So you just need to add in this dt factor in the Python code. That's all. And then a quick shortcut is to increase the PID controller gains based on existing solution for original speed of 1 and simultaneously reduce dt, both proportional to speed increase. So yeah, you have the original solution for speed 1, then you simply multiply the gains by 10 and decrease the time step by 10. And you get the same controller and same effect on the system. But in reality, you will not have an existing solution to fall back on. And you must tune the PID gains from scratch. So that's why I give this assignment to ask you to start from initial gains of 0, and then use twiddle to tune the controller to the best performance. So the tasks are first is for a speed of 1. You tune 4 controllers, P, PI, PD, PID, and plot the results. And for task 2, you can see that it's unstable for time step 1, the default time step, and then you adjust your DT and until you achieve a low tracking error. So any questions on the assignment?
I had a little question about you control 2 things like the deviation and the orientation of the vehicle. So sometimes you need to weight them differently, I think, which is most important, to stay close to the road or to orientate the vehicle in the same.
Oh yeah, so the program is trying to minimize the average error. That is, if you look in the program, so let me look for that track. Here's the track. So the error is the final error is computed by adding up the per step error. So that is you have the actual trajectory is a set of sequence of points because of the finite time step. So it maybe looks like this. So that's the actual trajectory. And then you compute the average of the cross-track error based on this obtained actual trajectory. So this error is affected. So it is the distance to the center of the lane. But to reduce the error, you need to adjust the vehicle heading in the process. And it's a nonlinear equation. So I mean, it is Carla said something that's reasonable. If you have 2 objectives, you should put a weight on each objective. But in this case, the aggregate, the total error is actually a function of both factors. One is the heading, one is the distance to center of the lane. Are you happy, Carla?
Yes, yes, they are connected, of course, but you can have a slalom driver who still are on the track. When it oscillates around the track, it could be better than just try to follow the track. If you are driving in the forest, for instance, with a slippery car, you never follow the track with the car's orientation. It's always a little bit off.
Yes, I just thought of something. So you may introduce another error definition, which is the aggregate heading error relative to a heading of 0 as theta. So and then it figures in the factor. First is the distance to the track. Second is the heading. Always left and right oscillating, or is it going straight most of the time, right? So that's 2 factors.
Yeah.
Yeah. But in this definition of error, we're just counting the distance to the center of the track, to the center of the lane, which is affected by heading and the distance. Okay, I think we can take a break and come back. Let me stop the video so we have a separate Okay, so the assignment is, yeah, you tune the controller, PID controller. Task 1 is to tune it. Task 2 is to increase, change the track shape to a round circle, and then tune it. Task 3 is to set the higher speed. So programming tips. So one way is to set the DP array to control whether it's a PID control or a PD control or a P control. So the 3 parameters are P, proportional, derivative, integral. Or you can set the small array P to all zeros, and then you can use this code. So you can iterate over all 3 indices to get a PID controller. You can iterate over only the first 2 indices to get the PD controller, and so on. Yeah, so it's just a small trick. It's no big deal. And I provide these 2 racetrack programs. These are from the Udacity assignment. So you should watch these Udacity videos for more
Videos implementation of twiddle.
for additional details. So, but the videos are very short. So assignment date is today, and I give 2 weeks for finishing the assignment. So I think it should be enough. Okay, any questions on the assignment? Hopefully this is simpler than the previous one. Yeah, so the previous one, I think many people had difficulty because they were not familiar with the frameworks, PyTorch and Colab and so on. So this one is more of starting from scratch. There's no frameworks used. You just use Python to write a program. Say something, Carla?
Not on the lab, maybe. If there are some questions, I will try to answer them, of course. And as we all do. I just mentioned also I started to prepare this deep reinforcement learning part, which will be following maybe next week or so. So I added the slides and so on. And I noticed you, Songwa, also have some slides. So like last year, I had some kind of introduction, a little bit easier. And then you had a little bit more detailed. I don't know if you run similar this year, but I think so. And they are pre-recorded, so you can start watching them whenever you want. And then I will use the lecture time for playing around and answer some questions and so on. So you can.
Where is it?
A new module. Yeah. So if you scroll down a little bit, so I added those slides there now, so you can have them. And the videos are on Play. So RL intro is, for instance, 5 short videos, so you can see them quickly, I hope. And then they are a little bit more complicated, this 1, 2, 3, 4. So we will talk about the details, me and Songo, and then present it for you, I hope.
Yes, very good. So yeah, so today I finished the control lecture, lecture 6. Next lecture, I'll finish planning. And next week, we'll start reinforcement learning.
Yeah. So I don't know if my lectures should be before your lectures, or after, or
maybe after, so you can describe the assignment in the latter hour of the next week's Monday's lecture.
Yeah. Okay.
Yeah.
So there will be assignment 4, yes.
Yes, there may be some overlaps in the assignment durations. We're running a little bit short of time.
Yeah, sure.
So, but we'll keep the assignments doable. Keep it simple so you can finish. Yeah.
Enjoy this. So I think the toughest was the first one, as you said. So, but we also provided some help, so you had more or less the source code available. But after some time, it was still difficult. So, but I think this your twiddle and all these things is much easier. Just particularly if you know control in advance a little bit, so it shouldn't be too difficult. And don't hesitate to ask if you have some questions. So, and then yeah, maybe me and Songo talk together how we deal with this next reinforcement learning part, not wasting your time with our...
We cannot see the slides in the module about reinforcement learning.
Oh, it's in the I can see it. If you click in modules and scroll down.
Yeah, I did that. But
I now published them. Sorry, I forgot to publish. Okay. So they are now published.
Okay, thank you.
It was only for Songo first.
I see.
So, but there is some overlap with Songo's lectures in the similar topics. So we will see what order is best. But feel free, you have the videos, you have the slides. So if you have some time over a rainy, gray day, you can start with those.
Yeah, in fact, for the reinforcement learning part, I am gonna be lazy and reuse many of my previous videos because I thought I explained things pretty well. So you can watch ahead if you like. Yeah.
Yeah. So I think it's an effective use of the teachers that we have this pre-recorded, and then you can spend some time to help and to make practical examples and so on. So I hope you. I have to agree, it's a little bit boring to watch pre-recorded videos for some strange reason. If you know it's not in real time, so to say. I don't know why, it is some kind of feeling. But like a recorded concert or football, soccer match, or the real stuff. But it's effective anyhow, and you can stop and you can watch it anytime and so on, and rewatch it if you want to.
I think the recorded videos, only one problem is that we cannot ask questions, right?
Yeah, that's right. So ask questions in forums or send us an email. I think it's better to ask in the forums. So I try to reply quick if I can.
Yeah. Okay, sure. Thank you.
So don't hesitate to fill the forum with questions. And I also will have some, maybe the last hour or so of this, what to say, yeah, of the time for questions and playing around with examples and so on. So you have a deeper understanding of what this is about. But I think the lectures, my lectures are a little bit more basic, not so advanced, and Songo is a little bit more advanced and detailed.
Yeah, so the videos, I'm actually going to play the videos in class for the reinforcement learning lectures. So you can always raise questions during the lecture.
Yeah. So I will be there also during this time, which I have scheduled. So if there are something I can just, I don't know if I should play it during the lectures. Does it work well? You try this?
Yeah, why not? I think it's a good idea.
Yeah, and then if someone asks something, then we just can stop the video and talk about it. That could be a good idea. Yeah.
But can we do a mix of this? Because you also mentioned something before, Kali, that if we watch some of these videos before the lecture, then we can use most time of the lectures for discussions and other things.
Yeah.
So how can we balance this up?
Yeah, that's right. So maybe we say that you watch the first hour or so, and then we watch the last hour of the lecture films. During my lectures, at least. I don't know about Songa. But then we have the second hour for discussions and playing around and questions and so on. So I hope that will be enough. Is that a good idea? So you watch the first easy hour by yourself, and then when it becomes a little bit more advanced, maybe then we are watching this second hour together, and then we have a lecture with practical examples and so on for the second hour on the schedule. I will send an email because so everyone knows this, if you think it's a good idea.
I'm not sure. Let me think. Okay.
Because the lectures themselves are like 2 hours, so if you just watch them, you don't have any time over for discussions.
Yeah, but let's do the online in-class viewing of the videos, and let's see how it goes. Based on student feedback, we may adjust the teaching method. But I think it's a good idea to watch the videos because the last year's lectures were I think I did a pretty good job.
Yeah, sure you did. So and also there are some changes as well. So it's good to be there to tell the students that, oh, this is about, for instance, some lab which is not the same this year. So it might change from last year or so.
Yeah, starting from this MDP planning. So lectures 6 and 7 will be updated significantly. But from lecture 8 to 11 should be pretty much the same. Yeah.
Yeah. But should I watch kind of my videos before yours or in the middle somewhere or something?
Yeah, my lectures are 2 hours.
So I think, like you said, imitation learning and those things are a little bit more advanced maybe than my first lectures, at least. So we order them in some kind of logical order, which one is best to see first and so on.
I moved the imitation learning stuff to the last in this year's lectures. So I think if there's no objections, we can have a lecture of 2.5 hours instead of 2 hours to accommodate the additional videos by Kala for a few times. I think that should be okay because most people watch the recorded version anyway. Yeah.
So they can watch it some other day in advance, maybe in double speed or something. So, and then we have after the ordinary 2 hours, then which I will watch and ask or reply to some questions if they appear, and then we have an extra half an hour after the lecture, after the scheduled lecture for questions. Does it seem good?
Yeah. Okay, so that's it for today. Good luck on the assignment. Any more questions? Okay, let's stop here. Goodbye.
Oh, thank you. Bye-bye.
Sure.
Bye-bye.